Hi everyone, and welcome to the second of 4 videos going through some past exam questions on the topic of acids and Ka. We're looking at some more weak acids here. We've got butanoic acid. First thing, it's asking us to write the expression for the acid dissociation constant. So if it wants us to write Ka, remember it's just the equilibrium constant for the acid dissociating. So it's going to be the H plus ions. It'll be the negative ion, we can just copy it from here. CH3, CH2, twice COO minus, and then the acid concentration of the acid itself. It will always want you to write in the correct formulas, don't do A minus and HA. It then wants to calculate the pKa. Well, the pKa is the negative log of the Ka. So the Ka is 1.51 times 10 to the minus 5. So it's a negative log of 1.51 times 10 to the minus 5. So let's just work that out. It's going to be around 5, isn't it, by looking at it? So log of 1.51 times 10 to the minus 5. So it's going to be 4.82. Right, then it wants us to calculate the pH of the butanoic acid. So for this one, this is going to use the same kind of trick that we saw in the previous video, where we're going to rearrange our Ka. Okay, I'm just going to be lazy here because I've already written the Ka properly up here. I'm going to be lazy here and do it this way. Do you remember we said that when the acid dissociates, you get one H plus ion and one A minus ion. So the concentrations of these two are always going to be equal. So we're turning this into H plus squared. Therefore, we're going to rearrange this. We want the pH, so we want the H plus concentration. So H plus squared is going to be Ka times HA, and therefore the H plus concentration is going to be the square root of Ka times HA. So the H plus concentration is going to be the square root of the Ka, which they gave us up earlier on, 1.51 times 10 to the minus 5. Put that in. And the HA concentration is 0.25. So therefore the H plus concentration is going to be, let's work this out, so 1.51 times 10 to the minus 5 times 0.25, and do the square root of that. 1.94 times 10 to the minus 3. And therefore what we're now going to do is we're going to say that the pH is the negative log of the H plus concentration. So it's going to be the negative log of this. And we're expecting a number of around 3-ish. So if we do the log of that, 2.71, 2 decimal places. Yeah, it usually wants a pH to 2 decimal places. Okay. Remember, it's coming out as negative on my calculator just because I didn't put the minus. It should be minus log. We're never going to get, well, we could, but it's unlikely that we're going to end up with a negative pH value. Not for a weak acid. Okay, hopefully that's something that you want to get fairly comfortable with. When it's asking you for the pH of a weak acid, this is a standard question where you go, I'm going to make it H plus squared, I'm going to rearrange it to get this square root rearrangement. It does want to be one that you end up getting familiar with. Right, then we've got a couple of questions here, looking at some ionic equations. So we want butanoic acid reacting with magnesium. So here, once you get more comfortable with these, you can start doing a little bit of it in your head. So you can say what's going to happen here is butanoic acid is going to react with magnesium. I'm going to make the magnesium salt of butanoic acid, aren't I? So what's going to happen is the butanoate ion is going to end up cancelling out from the acid, and it's going to end up cancelling out from the salt. So I'm going to end up with the H plus ions from the butanoic acid reacting with magnesium to make magnesium ions in the salt, and then hydrogen gas, aren't I? Yeah, and the negative ion from the acid and the negative ion from the acid is cancelled out. Okay, And then this isn't balanced, is it? I'm going to need to have 2 of those. Okay. Now it wants us to do the ionic equation for butanoic acid and sodium carbonate. Okay, importantly, aqueous sodium carbonate. Most carbonates are not soluble, so we can't separate them into ions and cancel the ions out in the ionic equation. But if they're telling us here that the sodium carbonate is aqueous, then that is going to make a difference. Okay, so again, I'm going to get the same thing here where the butanoate ion is going to cancel out. Okay, so again, I'm going to have the H plus ion from the butanoic acid. It's going to react with the sodium carbonate. It's going to make sodium butanoate. So the butanoate ions from the acid and the sodium butanoate are going to cancel. And the sodium ions are going to cancel from the sodium carbonate and the sodium butanoate. So I'm going to have the H plus ions coming from the acid. I'm going to have the carbonate ions coming from the carbonate. And what would be the reaction here? It would make sodium butanoate plus water plus carbon dioxide, wouldn't it? So here again, in terms of balancing it, I must have had 2 H plus ions. It balances the H plus and it also balances the charges, look. So 2 plus and 2 minus, and there's no charge on this side. Right, last bit here is another acids-base pairs thing. So we've got methanoic acid, they're adding it to butanoic acid, a reaction takes place, what's going to happen? Okay, so here, we're trying to work out which of the two is the stronger acid. Okay, what do we use to work out the strength of the acid? We use the Ka values, don't we? Okay, remember Ka is the equilibrium constant for the acid dissociating. If we go back up here to Ka, if I've got a big value of Ka, it means I've got lots of these things. So a bigger Ka means a stronger acid. So butanoic acid is 1.51 times 10 to the minus 5. Methanoic acid is 1.82 times 10 to the minus 4. So the methanoic acid has got the higher Ka value, so it's the stronger acid. So this is going to be the acid, and the butanoic acid is going to act as the base in this case. So the methanoic acid is going to donate a proton to the butanoic acid. So it's going to be H2 plus, and the methanoic acid is going to end up without its proton. So if this was the acid, this is its conjugate base. So let's call that base 1 and acid 1, because those two are a pair. And therefore this has got to be base 2 and acid 2. Again, remember, an acid and a base on each side of the equilibrium, and a 1 and a 2 on each side. Okay, carrying on. The next question that I want to look at here is a bit of an unusual one. Okay, it's quite wordy. This is literally just waffle, I'm not going to bother reading that. But here's where the question starts. So we've got propionic acid, it's a weak acid. Here's its equilibrium for it dissociating, fine. A student wanted to prove that it's a weak acid. They had access to a pH meter and they knew what the concentration of the acid was. Explain how they could prove that it's a weak acid by taking a single pH measurement. Okay, and then show how they could calculate, this is the clue, show how they could then calculate Ka. Well, the fact that we're trying to prove it's a weak acid, so what does a weak acid mean? A weak acid means that it partly dissociates, right? Not fully. So how can we prove that it's a weak acid just by measuring the pH? Well, it's almost, if you approach this from a different aspect, rather than proving that it's a weak acid, what you can do is prove that it's not a strong acid. Prove that it doesn't fully dissociate. Okay? If it did, so what we can say is, if the propionic acid is a strong acid, the pH, you can calculate the pH by just saying, well, it's going to completely dissociate. If it's a strong acid, if that's the concentration of the propionic acid, then that will be the concentration of the H plus ions, because it will completely dissociate. So you could then calculate the pH by just taking the negative log of that. Okay, and so if we work that out, do the log of 0.1, comes out as 1. If I do negative log there, we get a pH of 1. So what we're saying is, if it was a strong acid, its pH would be 1. So the student can prove that it's a weak acid as the measured pH would be greater than 1. Yeah. So if you measure the pH and it's not pH 1, it proves that it's not a strong acid. Yeah, it proves it's a weak acid. And it would be a higher pH, wouldn't it, if it's a weaker acid? Okay, so we've done this bit. How could they then calculate Ka? Right, well, let's write out Ka. So Ka is going to be H plus CH3, CH2, COO minus. So that's how you do Ka, but remember, if it's a weak acid, we can turn it into H plus squared. Right, and then we know what the concentration of the acid is, don't we? Because we know it was 0.1. So it's going to be the concentration of H plus squared over 0.1. And then the concentration of H plus, you can get that by doing 10 to the minus the pH. Okay, and we don't know what the pH is, but he was going to measure the pH. Okay, so therefore, once you've measured the pH, you can do 10 to the minus pH to get the H plus, put that in there, square it, divide it by 0.1, and you've calculated your Ka. Okay, so from the measured pH, you could say here. So it's a strange question, this, because you're not actually doing the calculation, you're just describing how to do it. Measure the pH, do 10 to the minus pH to get the H plus concentration, square that, divide it by the acid concentration, and then there's your Ka. Okay, so you have described how to do it. Okay, last couple of questions here are just more practice of the same types of things. We've got acid-base pairs again. We've got nitric acid and propionic acid. This is one they're expecting you to know. They're expecting you to know that nitric acid is a strong acid. So it's going to donate its proton here. So we're going to end up with the proton going onto the propionic acid, and we're going to end up with the nitrate ion left. Label the acid-base pairs. So this is the acid, this is the base. And therefore, if that's the acid, this is its conjugate base, because remember there's a difference of a proton. And so let's label that base 1 and acid 1, and therefore this is base 2 and acid 2. Okay, write an equation for the reaction of propionic acid and magnesium. So it's just the equation this time, not an ionic equation. So propionic acid we can see is this. It's going to react with magnesium. It's going to make the salt, so we're going to end up with... You can write it with the charges in or without, it doesn't matter. So let's just write the charges on. So that's going to make that ion, and it's going to make the magnesium 2 plus ion, isn't it? So I'm going to have 2 of those negative ions, so that's going to have to be a 2. I'm going to lose the 2 hydrogens as hydrogen gas. Okay. You could either, like I said, either put the charges on or take them off, it doesn't matter. But don't do half and half, don't do one charge but not the other, for example, because then it's not balanced. Right, and then read the question really carefully. What always catches people out is, oh, so write an ionic equation. Oh, okay, it's not an ionic equation for this. Write an ionic equation for a different reaction, for propionic acid reacting with sodium carbonate. Okay. So, hang on. If we go back to the sheet we did before, we did an ionic equation for butanoic acid and sodium carbonate. Okay, now we're just doing propionic acid and sodium carbonate. Well, from here, the ion from the acid cancelled out, didn't it? So it's actually going to be exactly the same reaction. Okay, we can just copy it from here. Okay, the fact that it's propionic acid instead of butanoic acid is not going to matter, because that ion from the acid ends up cancelling out anyway. So once you get the hang of these questions, you find the same things keep coming up. All they've done is changed it from butanoic to propionic. Okay, and that's why it's worth practicing these types of exam questions, because when you get to your exam, you're like, I'm sure I've seen this question before.